It's time for everybody's favorite day of the chapter. We are going to apply the math which we've been practicing for so long and use it in this wonderfully meaningful way. So let's go for it. All right. First example. We are in Cape Town, South Africa, and we have a chart of our temperatures in Celsius, right? Because most of the world uses Celsius and not Fahrenheit like us. So, all right, Celsius, whatever that means, right? I think it's a type of energy drink, Celsius. Anywho, let's go for it. So we've got this each month, the average temperature for that particular month. Now, you may notice something a little weird here. In January, it's warmer than in July. What? What kind of weird Oh, that's right. This is Southern Hemisphere, right? So everything's like backwards in the Southern Hemisphere. Toilets flush counterclockwise, I do believe. I don't know actually for sure. But I did ask somebody from Australia that follows Riverdog Jenny on the gram, and they didn't really know what I was talking about when I asked them if their toilets flush backwards. They probably just thought I was crazy. So let's hop to it. When we're dealing with these application problems, and you can kind of see that this looks like a cosine wave, right? This portion of it looks like a cosine wave. So what kind of points are we going to work with here? Well, there is a way to do it with like a regression model on your calculator, but we're gonna stick to more so like paper pencil type with a little bit of calculator action. So when I'm dealing with a graph, I'm going to look at my max points. So like that'd be a max right there, and this minimum here, and I can use those to create this cosine function just from those 2 points that should follow it pretty well. So if I'm looking at my T chart, we got January, and the other one looks like it's a 7. That is July, right? So we're starting our numbers and be like 1, 2, 3, 4, 5, so on and so forth for our months. All right. So that also says that right over here, if you didn't see that. All righty. So for January, I have 28 as my max. For July, I've got 15. That's my min. Perhaps I could find a midline from that. So if I take my max, which is 28, and add my minimum and then divide that by 2, I get 21.5 when I do that. So let me jot down, or let me draw in that midline there, just a little bit above. This is going to be somewhere right around, actually it looks like that point was labeled on there as a 21.5, so it goes right through it. Cool. So there's my midline. That'll be helpful for my equation here, right? Now, what's another thing, and I'll label that midline. How about my amplitude? What would my amplitude be here? Well, I could take my amplitude from that midline up to 28, that's going to be 6.5, and the same would go for going down to 15, 6.5, so 6.5 is my amplitude. And what's my period? Well, the period is how long it takes to repeat itself. 1 year, that's 12 months, right? Well, that's everything that I need. Oh, hold up. Phase shift. We'll address that in the equation, but that phase shift, we're shifting, if we're doing a cosine function, a positive cosine, we're moving to the right 1 because January is a 1 in our equation, okay? And we're going to be in radians with this. So for my period, I want my period multiplier now. So I would take 2 pi, divide it by 12, and that gives me pi divided by 6. I have everything I need pretty much here for this wonderful equation. So I have y equals, and then my amplitude is 6.5 cosine. Since I'm starting above the midline with January, that's going to be a positive cosine function, right? And then inside here, I've got pi divided by 6 for my period multiplier. And then we'll use T. And actually, why don't I do temperature T and then of time. It's a little weird, right? But T being your temperature, capital T, and lowercase t being your time. I guess, yep, cool. We'll go with that. So then I would have T, and then it's a shift to the right 1 month, right? So minus 1. And then my midline up 21.5. So this would be my function. I'm going to go ahead and leave it like that. We could multiply out the pi over 6. We're going to leave it like that for now. That's a beautiful, beautiful function there to model what's going on. You can actually plug in a particular month, and it should give you a pretty darn accurate answer there based on the month average, or maybe where you're at in the month, maybe halfway through the month, almost over with the month, things like that. You can use this to predict then what the heck's going on with that temperature. So that's it for our first example here. We're going to pop into another example. I do enjoy this particular example that deals with the Bay of Fundy, tides and things, okay? All right, so I'd highly suggest checking out that video on the Bay of Fundy. It's crazy. It's the largest tidal change in the world, perhaps even the universe. We don't know for sure. But anyways, at low tide, it's a depth of 2 feet. And then at high tide, just 6 hours and 12 minutes later, it's 58 feet deep, right? That's a crazy change in water depth. So we can actually model that with a sinusoidal function, whether it be a cosine or sine function, right? And the thing is that it's pretty helpful to know when these tides or what the depth is going to be if you are taking your boat out, say, to go fishing, not for just for fun, but like maybe that's your livelihood, right? People do that to make a living, right? You got to feed people. So you have to know when you're going to be able to get your boat in and out of this bay, because at 2 feet, most boats won't be able to leave the Bay of Fundy at that depth. So you have to know what's going on and when. And it's not like it's a perfect 6 hours, which would be a fourth of a day. It's 6 hours and 12 minutes. So throughout the year and out the month, the timing of this changes, okay? So let's jot some things down. So time in at, let's say, time 0, our depth will be at 2 feet, okay? And I'm going to change this to depth. Cool. And then it says, and 58 feet at high tide, which occurs 6 hours and 12 minutes after low tide. So if we're talking, let's say hours here, okay? Depth in feet. So if we're talking hours, well, 6 hours and 12 minutes. 12 is what fraction of 60 minutes, of an hour? Well, 12 over 60 would simplify to 1/5, which is 0.2. So 6.2 hours. Okay. I don't need to really use hours there because it says hours. Okay, and I guess I don't need to put feet either since I put that in the up at the top there. Whoop, there it is. Okay. So the depth then is 58 feet. And then another 6.2 hours later would be 12.4. And we would be back at low tide, which would be 2 feet. Okay. So at this point in time, 6.2 hours later, it's going to be back up to 58. So it's going to start repeating itself. So it looks like when it's asking us in the next part, amplitude, period, and vertical shift, I'll leave our amplitude for now, but our period, we appear to have figured that out, 12.4 hours. Awesome. And then our vertical shift, we'll still need to figure that out as well. So let's start graphing this thing. I'm going to scale some things out here while I pause the video, and then we'll graph it together. So at this point in my scaling, it looks like, I'm really going to need that midline. So let's calculate that, shall we? I would take, and I'll do that over here. I would take 58 plus 2 and divide that by 2. That's going to give me, 60 divided by 2 is 30. So that will be my midline there, right? So that'd be my maybe another point that we could jot down here. 30 would be in the middle there, right? I think that might be kind of helpful. When would that be occurring? That would make sense to be occurring halfway between 0 and 6.2, which would be 3.1. So there's another valuable point that we could have there, and we could even also add that to between 6.2 and 12.4. So add 3.1 to that, and I would get 9.3. I would also be at 30 once again. Looks like now, so I've got my midline on there, right? I've scaled out my x-axis or my t-axis. We're looking good in this graph here. The last thing that I think we could also point out would be like my amplitude. My amplitude here is going to be 28, right? It's 28 above 30 to get to 58 and 28 below 30 to get to 2. Now, if I plot out my points, at 0, we were at 2. And I'm going to use blue here, the dark blue, because water and things. So at time 0, it was a depth of 2 feet, right, at low tide. Then 6 hours and 12 minutes later, or 6.2 hours later, it was at high tide, which was this point way up here. But as we know then, halfway through should be right there. And then down here at 9.3, and then back down to 2. So we're going to get our nice cosine graph. Let's see if I can handle this live. Woo! Woo! That was pretty good, except that fourth point there, I almost missed it, but I still got it. I feel like I still got it. I can even be like, hey, I totally got it. Okay. So there's my my cosine function there that would represent the tides. So I feel like at this point, we're ready to write our equation for this function. As we've already said, it's a cosine function, right? It appears to be a cosine. I mean, you can write it as a sine function, but clearly looks like a cosine function that's been reflected here. So let's do that. So I would have let's see here, depth of t. So d of t, the depth as a function of time, would be, let's see, we said it was going to be a negative cosine, right? So negative, my amplitude is 28 cosine, and then my period was 12.4 hours, so we're actually not ready yet. We're going to take 12.4 divided, 2 pi divided by 12.4. I'm thinking that I'm just going to leave it like that pretty much. How would we just go with pi divided by 6.2? I think that's fair enough, right? So I just simplified the 2 and the 12.4. So pi divided by 6.2. And then I'm going to have t. And do I shift it all? No. So I don't actually need that extra set of parentheses. I'm starting at time 0, right? We're not starting at like 1 like we did on the other one. Need some Norton action. And then, let's see here. We got plus, right? And our midline was at 30, right? That was our vertical shift. And it did ask for that right here. So that was up 30. Okay. I like it. I think we're pretty solid there on our equation. So let's think about answering some questions here, and then I want to do maybe a little bonus action with this one because I find it quite interesting. So what is the depth at 2 hours? Well, how can we figure that out? I'm going to bust out my T84, hashtag YORO, and I'm going to plug this bad boy in. Now remember, we did calculate this with radians, so we do want to be in radian mode when we're figuring this out. So make sure you adjust that to radians right now before you plug it into your calculator. All right, so I've got my emulator up here. I've got negative 28 cosine, and then pi over 6. I made a mistake there. It should be 6.2 times 2. So let me second insert 0.2. There we go. I put that in parentheses there just because its own fraction. I don't have the fancy fraction feature here, so it makes me feel warm and fuzzy inside to have that grouped in parentheses. Not really necessary, but whatever. And then I got the plus 30. So we should be good here. 15.189, so 15.19, 189. We'll go with 189, sure. 15.189 feet after 2 hours. Okay. So that's somewhere right around here, it looks like. Yeah, right? There's our ordered pair, 2 comma 15.189. It looks right on the graph. I like it. Now, it says if a medium-sized boat requires at least 20-foot depth. All right, that's often called a draft, a 20-foot draft, meaning what comes out the bottom. At what times can a boat pass through the bay? So when can the boat pass through the bay here according to our model? So how are we going to do that? Why don't I pull up my calculator again, but I'm going to throw this into my, my grapher, okay? All right, so I've got it plugged into the y equals here. And then, be careful with your parentheses, all that good stuff. Pi over 6.2, right? Don't make the mistake I made where I just did 6 at first. In my window has changed to, I went with -2 for my x-min, just so I see the axis. And then I went with 15 because at 12.4, that's our full period, so I just went a little beyond that. And then for my y max, I went with 70 to go a little bit above our 58 foot depth. And I went with -2 again so I can see the y-axis. So you can see both my X and Y axis, lovely. Looks just like the graph that we have sketched. So we said, when will it be a medium-sized boat is, was it 20 foot depth? Okay. So how about we go back to our Y equals, and we've done this before with various functions, and we'll throw in a horizontal line of 20. And let's graph that. So we want to know, when is the depth greater than that, right? So that that boat can pass. So let's find some intersections. So second calc, and then we're going to go to intersect, which is 5. And when it says first curve, I'm just selecting the lines, but this way it'll be, if I select both of them and then I go over closer to the one that I want first, right? And the reason for that is because there's 2 intersection points. So if I selected these 2, even though the 2 selections are closer to that point we have right there, if I moved over to the right, it would select the one on the right. So if I hit enter one last time for my guess, there we go, 2.37920. So at 2.379 hours, 2.379 hours, and then let's find the other one there while we're at it. Second calc, intersect. And then I just want to make sure I'm on that curve. So I'll show you what I mean. If I hit enter, enter, but then I just arrow over closer to this one, it's going to select that one. Be hilarious if it didn't. It looked like I wouldn't know what I was talking about. So I've got 10.021 after I round. 10.021 hours. So between that time frame, so we could say from it actually says at least a 20 foot depth. So 20 is cool. So we'll do brackets 2.379 to 10.021 hours. That's 20 feet to 20 feet and anything greater than that between that interval there for this one. Okay? So that's when a medium-sized boat would be able to pass through that right there. All right. Now, I think this will be our last problem we do for this one, but I do want to talk about a couple of other things here when talking about tides, because I find it kind of interesting and maybe a little connection to calculus, okay? So if I'm looking at this sinusoidal curve, right, this cosine function that we have graphed, let's think about this. It's a bay that we're talking about, or if you had like an inlet or something like that where the water is flowing in and out. When do you think that water is flowing at its fastest rate, right? Let's think about it as like almost like an inlet, like water is going in and out of there. When is it flowing at the fastest rate? Well, we can think about this of just like the general slope aspect of things. I'll go with orange now. But at this point in time, if I were to draw like what the slope and estimate of the slope here, perhaps it would be something like that one right there. But now, say at that 2-hour mark that we were talking about, if I were to think of like what's going on at that exact moment of time and put like a line that's tangent to it, right? That would give me like an idea of what the slope is at that given time. And then when you see us getting closer to like say where the tides are changing, like it's transitioning from low to high tide, or like getting to that aspect, well, now the slope is a little more mild. And the same would go up here. If I'm just before high tide, absolute high tide, we'll say, I've got, let me get that up a little higher there, more tangenty. I see a pretty mellow slope, and at high tide, at that exact instant, my slope would be, well, I couldn't get it quite there, but my slope would be at basically, it would be at 0 at an instant, right? and then the water starts flowing out. So at one point in time, the water's not moving at all, and then it starts moving again. But at that midline is where my slope is the steepest, right? The water movement is at its fastest when we're talking about, or especially noticeable in some inlets. So follow a story about tides, and then we'll end this thing, I promise. We were in Florida and West Palm Beach, and we were on the intercoastal, and we were thinking about going to this place called Peanut Island. Now, we wanted to take our paddle boards that we brought with us. They were inflatable paddle boards, and we wanted to launch from where my grandparents' condo was and take our paddle boards to Peanut Island. But it was a bit of a trek, so we weren't sure if we'd really be able to make it. We were talking to a fisherman on one of the docks at a local restaurant and asking him about some things, and then brought that up, and he's like, hey, why don't you use the tide charts? And we're like, what do you mean? And he's like, well, when you're going from low tide to high tide, when the tide is going out, meaning you're approaching low tide, the water is being drawn out of the inlet, which would carry you from your location to Peanut Island, like a river current. And then when we go from absolute low tide and the tide starts coming back in, meaning we're transitioning to high tide, the water is coming back into the inlet. So we basically went with like a river. So if you think of the inlet there as a river, as I was saying, to get to Peanut Island. Here's my info, my drawing here. We're going from the condo to the island. We're going from high tide to low tide. So that water is being carried back out to the ocean, right? Now, when we go from low to high tide, the water is coming back in from the ocean. Water is coming back in from the ocean and filling up that inlet. So then there's a current that would push us back towards the condo. So we didn't have to fight the current. We got to actually just kind of chill, and it would take us. I mean, we'd paddle a little bit, but it was something that would help us as if you were going in a river that changes directions 4 times a day. And that was kind of fascinating that we were able to use that and make our trip a little bit easier when we were doing the paddle boards there. And we just looked at the tide charts, which do change daily. As you can see, it was like 6 hours and 12 minutes in this location. It's pretty standard where it's going to change a little bit. It's not going to be a perfect 6 hours and happen 4 times a day. But we were able to look at that, pick the day that worked out best for the timing and the weather and stuff like that. And we were able to make that happen. So that was pretty darn cool. A cool use of tides. And I could have, if I wanted, use those tide charts, do a math problem, use my T84, YORO, to also, I could have figured it out that way on my own. But I just used the newspaper or the internets to figure out the tides. All right. Well, I hope you guys enjoyed that story. We'll end it here. I do appreciate you sticking around. And if you have any questions, feel free to ask. Otherwise, have a wonderful day. America, freedom, rock and roll. YORO, Costco, and Riverdog Jenny on the gram. See ya.